Hello, I hope you guys can hear me. I'm going to be doing calculus stream after a really, not really long time, but I think it's been weeks or maybe months since I did a calculus stream. I'm looking at my YouTube studio right now. I think last time I did it, it was back in July. It's September right now. I need to get more done. Okay, so this time I'm going to continue. Hopefully, I haven't forgotten too much. Right. Okay, I'm going to change the full screen. Uh, Now it works. Almost. Let's see how much it totes. Okay, so limits at infinity and horizontal asymptotes. Recall that limit of f of x to where x goes towards a is equal to L means f of x becomes arbitrarily close to L as long as x is sufficiently close to a. We can extend this idea to limits at infinity. For example, consider the function f of x is equal to 2 plus 1 over x. As the values of x gets larger, the values of f of x approaches 2. We say the limit as x approaches infinity of f of x is 2. Alright, so x goes closer and closer to 0. F of x gets closer and closer to 2, but never exactly touches 2. Informal definition, if the values of f of x become arbitrarily close to L as x becomes sufficiently large, we say the function f has a limit at infinity. Okay, if limit of f of x when x becomes arbitrarily large is L, no, if f of x becomes arbitrarily close to L as x becomes sufficiently large, or x becomes sufficiently uh, x goes towards negative infinity, we say the line L y is equal to L is a horizontal asymptote of f. For each function, evaluate the limit. Is it the website that's slow, or is it like I think it's both my computer and the website maybe, but I'm not sure. for each of the following function if evaluate these limits determine the horizontal asymptote. Okay, over here x gets closer and closer to 0, the limit would be towards 5, right? So f of x would be getting closer and closer to 5. Since it's square over here, then it's both infinity and negative infinity. So I need this most this. What about tan arctan? So if I go here, in a as for arctan, let me see if I remember it. So I have this, I have this, and I have a tangent. So this would be tan theta, where this is theta. And the hypotenuse is 1. So now let's say take all this, I take all this, and then say this is x, and this is the inverse. This here is tan x. And what happens as x gets larger and larger and larger and larger, this will get closer and closer to 90 degrees or pi over 2 radians. As for sine x over x, this I can't remember. I remember there's a proof for it, but I think you use the squeeze theorem. If I wait, let me see if it's on my website. It's going to take forever. So calculus. We need it says here sine x over x is 1. Wait, why did it say that error? It said some client-side error. Okay, never mind. Prove that sine x over x approaches 1 as x approaches 0. Suppose can be written as, okay, over here removing 2 and removing and dividing it by theta, and this limit as cos square theta approaches 0 is 1. So then by the squeeze theorem, this becomes sine theta over theta gets closer to 1. Right. Oh, it's towards infinity. I mean, this is towards 0, but towards infinity, like you have sine x, which is normally like this. But then if you're dividing it by x, or like later down the line, over the sine x will have the wave, but x gets larger, the wave will get smaller because you're dividing it by that number. Smaller and smaller and smaller and smaller. Thing in both sides. Smaller and smaller and smaller. You get the point. So yeah, it's 0 over there. And it says minus pi. Oh, for negative infinity, yeah. Minus pi over 2. And so what is this? Infinite limits at infinity. Like as x gets closer and closer to infinity, f of x goes to infinity. These are the formal definitions. Okay. The behavior of a function as x approaches positive or negative infinity is called the function's end behavior. At each of the function's ends, the function could exhibit one of the following types of behavior. Horizontal asymptote, it goes to positive or negative infinity. It does not approach a finite limit, nor does it approach positive or negative infinity. In this case, the function may have some oscillatory behavior. Okay, that makes sense. For each function, evaluate. Okay, for this, it's obvious. As x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x goes to positive infinity. And the case is opposite for this one. Yeah. Consider a polynomial function of degree n is more than 1. Okay. Factoring, we see that. So they factored this out. We see that. Okay, all of these cancels out. So you're left with a 1. And that multiplies with the nth a with x to the power of n. The function f of x is equal to 5x to the power of 3 minus 3x squared plus 4 behaves like g of x is equal to 5x cubed as x approaches positive or negative infinity. What's this? Determining end behavior for rational functions. For each of the following functions, determine the limits as x approaches infinity and negative infinity. Then use this information to describe the end behavior of the function. F of x is equal to 3x minus 1 over 2x plus 5. The degree is the same in both the numerator and denominator. Okay, over here, the degree in the denominator is greater. Over in C, the degree of the numerator is greater. So I think the numerator, like in C, the numerator will have a greater effect than the denominator. If the degree of the numerator is the same as the degree of the denominator, then x has a horizontal asymptote. The degree of the numerator is same as the degree of the denominator. Alright, that makes sense. If the degree of the numerator is less than the degree of the denominator, then f has a horizontal asymptote y is equal to 0. The numerator, if the degree of the numerator is lesser than that of the denominator, okay, then the denominator will be going to infinity. Uh, uh, if the degree of the numerator is greater than the degree of the denominator, then f does not have a horizontal asymptote. The limits at infinity are either positive or negative infinity depending on the sign of the leading term. What about vertical asymptotes like 1 over x? Unless you're figuring out end behavior, unless you're figuring out only about the horizontal asymptote. It's limits at infinity. So it's not talking about vertical ones, right? Also, I did not talk about slanting asymptotes. Maybe it has, but uh, for the following exercises, examine the graphs, identify whether the vertical asymptotes are located. It does talk about vertical asymptotes. Yeah, it talks about horizontal here, horizontal. It talks about vertical. Is a slanting asymptote over here, but I don't know if they talk about it. Identify where the vertical asymptotes are. Let's see. For the following functions, determine whether there is an asymptote at x is equal to a. Justify your answer. Yes, because 2 minus 2 would be 0. 1 over 3. I think over here it's a yes. Because you can write it like, what is this? F of x is x minus 1. The power of, you can write it like this, right? So yes, there is a asymptote. Okay, let's do the next one. That's the main thing the stream was about. Optimization. The basic idea of the optimization problems that follow is the same. We have a particular quantity that we are interested in maximizing or minimizing. However, we also have some auxiliary conditions that need to be satisfied. For example, 4.32, we are interested in maximizing the area of a rectangular garden. Okay. Certainly, if we keep making the side lengths of the garden larger, the area will continue to become larger. However, what if we have some restrictions on how much fencing we can use for the parameter? In this case, we cannot make the garden as large as we like. Let's look at how we can maximize the area of the rectangle subject to some constraint on the perimeter. A rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other three sides. Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? Garden is constructed using a stone wall, a rock wall, so one side of the garden, and wire fencing for the other sides. Okay, so there's wire fencing here. Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. And it has to be rectangle. So the area is, shouldn't it be area given x and y? Wait. Area is x times y. X times y, and then the parameter, the perimeter, 2x plus 2y. So, given 100 feet of wire fencing, so 2x plus y has to be 100. This is We are trying to find the maximum area, right? So then mm, fencing is 100. Then I can write y is equal to 100 minus 2x, right? And then 2y is equal to 200 minus 4x. So then parameter only by using x, it's gonna be 200. This is 200 minus 2x. X at max can only be 100. That means the fencing would just be one straight line. No, the wire fencing is 100, right? Yeah. Wait. Given determine x at max can only be 50, because then there is wire fence of 50 going up and wire fence of 50 going down. 2x plus y. No, not parameter. Not no wire. No, wait. Hmm. Oh, what is this? What did I calculate? It 2x plus y is 100. That's a wire fence. And the area is forget this. Forget all this. So the area is 2x and then 100 minus 2x. And then derivative of a with respect to x. 200x minus 4x squared. This is how much the area changes depending on the x. So if it's 0, then 200 minus 4 times 2 is 8 x is 200 over 8. $25. X better be 25. Maximum area when 25. Okay. Why does it say 100x? Oh, wait. This is not 2x. This is just x. which means this is 100 minus 2, but the final result would be the same. 4. Okay. Solving optimization problems. Introduce all variables if applicable. Draw a figure, label all variables. Determine which quantity is to be maximized or minimized and for what range of values of the other variables. If this can be determined at this time, write a formula, write any equations relating the independent variables, identify the domain of consideration, locate the maximum, minimum, maximizing the volume of a box. And open top box is to be made from a 24-inch by 36-inch. Open top box. Okay. Mm. Open top box. This is 24-inch, made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flap on each side. Oh, okay. So 26, no, 36, 26, pretend that's, is it 26? 24 by 36. 24, 36, and we have to remove squares of the same side, I assume. And then we have to fold these flaps to make the box. What size square should be cut out of each corner to get a box with the maximum volume? Okay. So let me just take all this and put them all here. So volume, it the side of the square, let's call it x. So square is going to be the area of the square. Let's just say area of square is going to be x squared. This is 24. Let's say this is width and this is a length. Length is the big side. Length of the box given x is 36 minus 2x minus x from the both side. Width of the box is 24 minus x from both sides. And then the height of the box given x is x. So you're going to fold up the flap. So then the volume of the box would be the 3 combined, the 3 multiplied length with height. Volume of the box. (36 minus 2x). 24 minus 2x. And then just x. And then this is 36 times 24. Hopefully I got the quantity right. 864. 864. And then 36 times 2. 72. And then 24, 48. 48x plus 4x squared. And then this is equal to x minus 72 minus 48 minus 120. For x cubed. And the derivative, we need to find the maximum, right? So the derivative has to be 0. 240x. 4 times 3 is 12. So 0. This is 0. Can I divide 846 by 12? 864, sorry. 864 divided by 12 is 72. 72 minus, is it 20? Yeah. 20x plus x squared. Now x is equal to minus b plus minus b squared minus 4 times a times c over 2a, right? That's the quadratic equation. Wait. Minus 4ac 4 times 72. 400 minus 4 times 72. And then If I take all this, put it in brackets, take all this, put it in a root, it 2a 400 minus 4 times 72. What if I subtract it? In both cases, the derivative is 0, right? So if I do 864 minus 240, not 2, minus, no, this is derivative. 840x minus 120 plus 4x cubed. I get a negative number, but if I do this, get a positive number. So the answer is 4.71. Yeah, 4.7 inches. Minimizing time travel. Okay. An island is 2 miles due north of its closest point along a straight shoreline. Visitor is staying at a cabin on the shore that is 6 miles west of that point. Let's try to understand this. An island, shoreline, 2 miles. A visitor is staying at a cabin on the shore that is 6 miles west of that point. I think the shoreline is like this. And then there's a cabin here, which is like 6 miles west. This is east. There's a cabin here, which is like 6 miles west. The visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims. So runs 8 miles per hour and swims 3 miles per hour. Swims 3 miles per hour let's call it distance. Wait, hold on. An island is 2 miles due north of its closest point along a straight shoreline. Visitor is staying at a cabin on the shore that is 6 miles west of that point. No, wait. 6 miles west of this point. Wait, I think I do it wrong. I think I'm imagining it wrong. So cabin is here, and then there's 6 miles. Then the shoreline continues. How fast should the visitor run before swimming to minimize the time it takes to reach the island? Let me just see the picture they provide. Cabin. Okay. So 6 miles. All right. Cabin, 6 miles. Island, swims 3. So, how far should the visitor run before swimming? Okay, so he could run. Uh, if x is the distance he runs, distance ran, and y is the distance swam. So here he runs. He is, wait. So he's running and then he swims. So x, y, x, y. Two. Now, in order to reach this, how should I define this? Yeah, 8 miles per hour swims 3 miles per hour. X is the distance run. We need to minimize the time it takes. If it runs 8 miles per hour, so time running, that's the time it ran, is x divided by 8, right? And then time swam is y. I should like do it here. Time swam is y divided by 3. We need to minimize the total time. So time total is x over 8. plus y over 3. And then y also, okay, y is equal to 6, no, y squared is equal to 6 minus x squared. So it's this distance plus 2 squared. So this squared plus this squared is y squared. That would mean y is equal to root 6 minus x, 6 minus x plus 4, which is 6 times 6 is 36, minus 6x, then add them, plus, so then 40. Now what? No, I think this is wrong. Wait. I don't need this. I need to write it in terms of x. Yeah, actually that was correct. Because I'm going to replace y. So t total is x over 8 plus all this over half. Oh, it says my OBS disconnected. It says my OBS disconnected. Wait, hold on. I'm just checking if it's still active. I'm just checking my stream. It's loading really slowly. Then if it's still working, then I will continue my stream. Otherwise, I will start a new one. My stream, it's loading really slowly. Then if it's still working, then I will continue my stream. Otherwise, I will start. Hold on. Okay, it says it's live. My website. Okay, I think I'll just continue my string. Anyways, uh, Alt F. Okay, uh, derivative of this. So half comes here. Derivative of the outside minus the derivative of the inside. Times it by the inside derivative. Minus 12 plus 2x. So like this is equal to, so 3 times 2 is 6, so I will just write that. And we need this to be 0, right? 0. Yeah, I'm not in the mood of going through the end. I think I just need to know I'm heading in the right path. Okay, maybe I will go through the end. A minus. Is this correct? Let me see. I shouldn't have expanded 6 minus x. 6 minus x squared. If I didn't expand 6, wait, hold on. Six minus x squared plus 2 plus 4. Derivative of squared plus 4. This is half. Then this will be derivative of the outside times it by the derivative of the inside times it by derivative of this of the inside. That means, wait, let me just switch this. But I was heading on the right path, I think. This is this 2 and 2 cancel. $36. Isn't this harder? Don't I go back to square one? I thought it would be easier. So if this is 0, Yeah, the derivative is 1 over 8 minus half. Wait, oh, the half cancelled out. Wait, hold on. Yeah, half times derivative of this, so times 2 times 6 minus x. This is what I got. 0, you end up with this, this. Then squaring both sides of the equation, we see that if x satisfies this equation, then x must satisfy this. So simplifying would give this answer. Okay, I mean, I was on the right path, but I wasn't in the mood to do all of this. I don't want like really long questions. I just want, like, I don't like really long algebra. Maximizing revenue. Owners of a car rental company have determined that if they charge customers $P per day to rent a car where P is between 50 and 200, the numbers of cars N they rent per day can be modeled by the linear function N times P is 1000 minus 5P. If they charge 50 per day or less, uh, they will rent all their cars. If they charge 200 per day or more, they will not rent any cars, assuming the owner assuming the owner's plan to charge customers between 50 per day and 200 per day to rent a car. How much would they charge to maximize their revenue? So let's see if where is this? 1000 minus 5p minus 5p. Let's just say x. Okay. So if the price is what? The number of cars and they rent per day can be modeled by the linear function. Okay, so the number of cars they rent can be modeled like this. F of x is equal to f f uh what is f of 60? 700. Where is that? Won't they draw a line? Y is equal to, okay, 60. 50 is the minimum. How do I add slider? P not slider. How do I add a, how do I do like a piecewise function? So if it's 50, if they charge 50 per day or less, they will rent all their cars. How many cars do they have in total? Rent a car where? If they charge 200 per day or more, they will not rent any car. So 200, okay, 200 is 0. So the graph goes linear and then 0. But what about this? Do they have 750 cars in total? 50. This is equal. Like if P is equal to 50, you get 750. Since get, they have 750 cars in total, let's just uh, assume that. Assuming the owner plans to charge customers between $50 per day and $200 per day to rent a car, how much would they charge to maximize their revenue? So we need to find the maximum area of this. So f of x is equal to 750 if the price is less than or equal to 50 and 1000 minus 5p, let's call this p, 1000 minus 5p if p, if price so area of the graph is p price times let's do this, p times 1000, so x times y is p squared. The area is 0. The area is 0. And 1000 divided by 5. This is correct. Wait, hold on. Let me just make sure about one thing. No, 200. Wait. So they should keep the price 200. Okay, it says recorrection successful. Have to check again. Exactly 100 per day. Okay, wait. Just going to check in a few minutes. This is like the second time it's disconnecting. And nothing is loading as well. Okay, so it does seem to be working. Say add 0 over the inscribed rectangle within an ellipse. What should the dimensions of the rectangle be to maximize its area? So the ellipse is some. Here we have an ellipse. So it's defined with an xy point. Oops. It's defined with an xy point. Area would be, so this is wait, this is y. This would be x. The rectangle would be x with this, this, and this. So it would be x 4x. So area of the rectangle given x, y would be 4x times it by 4y. And 2, 3, 4. 4 times 4 is 16xy. However, it's an ellipse. X and y are like bounded, right? They depend on each other. So then that means y this is 2 y 8. Hmm. So then we only need area of the rectangle. We only need x would be x, I can put 4 inside. So 4. Wait, hold on. No, wait, what am I doing? No, now what? I should put the x inside. And then the derivative of the area is the derivative of the entire thing, which is nope. So this is the derivative of the outside. If I put half out, this would be 8. Times it by the derivative of the inside, which is 2x minus x cubed. And then the area has to be 0, right? So 0 is equal to, I guess we can take, hold on, we can do like this. We can like reduce the number of x. Uh, hmm. We need 0 is equal to this, then 0 is equal to this. That means x is equal to 2. So then 2 square would be 4. 4 divided by 4 is 1, and then we get 0, or x is root 2. Hmm. But wouldn't either of them work? Like if I put uh, x is equal to 2 here, then I get 0. X is equal to root 2. I think the answer is root 2. X is equal to root 2. Yeah. Thus x is equal to plus minus root 2. Solving optimization problems when the interval is closed or is unbounded. In our previous examples, we considered functions on closed bounded domains. Consequently, by the extreme value theorem, we were guaranteed that the function had an absolute extrema. Now, let's now consider functions for which the domain is neither closed or bounded. Many functions still have at least one absolute extrema as an absolute. So, for example, f of x is equal to x squared plus 4 as an absolute minimum of 4 at x is equal to 0. Okay, minimizing surface area. Let's do this. A rectangular box with a square base, an open top, and a volume of 216 inches cubed is to be constructed. What should the dimension of the box be to minimize the surface area of the box? What is the minimum surface area? So, a rectangular box with a square base. Okay, so it's square from top and bottom, and it's open from here. And then the volume of the box. Let's the size of the square is x squared, and then the height x height. This is 216 inches cubed. What should the dimensions of the box be to minimize the surface area of the box? What is the minimum surface area? Hmm. There is no limit to the height. Because x can go smaller and smaller and smaller, and then h can go higher and higher. Like x can go infinitely small. There should be more to this question. Uh, what should the dimension? In the following example, we will look at constructing a box of least surface area with a prescribed volume. It is not difficult to show that a closed-top box by symmetry among all boxes with a specified volume, a cube will have the smallest surface area. Oh, wait. They're asking for the surface area. Okay, yeah, I misunderstood. Uh, okay. So the area box, and it has an open top, right? What should the dimension be to minimize? Does the inside count of the surface area? Okay, let's assume it does. So x times h, that's one side, and we have four of those sides. So x 4x h, and then the surface area at the bottom, which is x squared. But I don't think it matters if you're like finding the minimum. I just need to see if the inside counts. Square donate surface area plus x squared. No, the inside doesn't count. Plus x squared. And then we need to minimize, so the derivative of the surface area of the box with respect to x. But h is like a variable. Oh yeah, this is 216 inches, so we can replace h. Then h is 216 upon x squared. This is 4 times 216 over x. And then 4 times 216, 864. If we are finding the derivative, x to the power of minus half, then minus half comes here. So then x to the power of minus 3 over 2 plus it with 2x. And then this, we need to minimize this. I can just divide this by half. 4, 3, 2 plus 2x. And then bring this to the other side. And then 432 divided by 2. Hold on. Dividing this by 2 and then dividing this by 2 again, so I left with 216. So 1 plus 3 over 2 is 5 over 2, I think. So in fraction, yeah, 5 over 2. So x, this square root it, root 216, and then this to the power. Wait, hold on, no. This is wrong. Squared 8.58, 8.59. Did I get this correct? Six times. Okay, I got this. 2x is. Wait, hold on. No, I did not get this. What is 6 times cube? Did I get this right? I made a mistake somewhere. Surface area, Asian surface area is this. What did I write? 4 times 216. Okay, so the derivative minus x squared. Why? This is x to the power of minus half, right? So the derivative is of this. Hold on. How did I get this? Am I getting this wrong? Minus half. This becomes minus 1. I don't understand. This Desmos allows derivative. Hold on. Uh, Derivative of 1 over x. Okay, I think I must have got this wrong. I did. Okay, yeah, I understand. Right. Hold on. Area, derivative of the area is what was 4 times 216, 864 x to the power of minus 1. So this becomes, and then this 2 plus this 2, yeah, 2x. And then we have to put this as 0. Uh, and then positive 2 cubed x is equal to this divided by 2, which is 4, 3, 2. Yeah, that's the final answer. Okay, I will end the stream here and do the exercises next stream. Also, I need to make a few changes in my stream. Yeah, I will see you guys next time then. Bye.